All right, so let's do some half-life problems. All right, so half-life, and I'm not going to get into, I couldn't if I wanted to, the physics and chemistry of half-life. I just know that there are different atoms. So, for example, carbon normally is carbon 12. Carbon always has 6 protons. And if you'll remember back in chapter 2, the atomic mass is the number of protons plus neutrons. So if the mass is 12 and there are 6 protons, then there must be 6 neutrons as well. So that's what we call, or what I call normal carbon. I don't know what other people call it. But there's an isotope of carbon, which isotope is just a atom that has more or less neutrons, a different number of neutrons. It is still carbon, so it is still 6 protons, but now its mass is 14. And so that means it has 8 neutrons. And so this is a radioactive isotope. It is unstable and it goes through something called decay. And so, again, your chemistry and physics professors can tell you a lot more about radioactive decay and beta and all the different kinds and stuff. But what you need to know is that when carbon 14 decays, which is releasing energy and such, it converts to nitrogen 14. Okay. Nitrogen 14 is a different atom. It has 7 protons. So it means because it has a total mass of 14, it will also have 7 neutrons. Okay. Again, more information than you need to know. But the time it takes for this process to happen, and it will happen for half of what's there, is called the half-life. Okay. So let's say that we had 100 grams of carbon 14. In one half-life, which is about 5,730 years, one half of that would decay to nitrogen 14. So after one half-life, or this 5,730 years, half of it would still be carbon 14, and half of it would be nitrogen 14. Okay? Let's say it went through another half-life. So this is like half-life number 2, another 5,730 years. Then half of what's left, half of this 50, will decay. So we'll have 25 grams. I didn't put that there, but that's grams of carbon 14. And we still have the 50, but the other 25 gets added. So now we have 75 grams of nitrogen 14. Okay. And because it's been 2 half-lives, you would add 5730 together, 5730 times 2, or 5730 plus 5730. And that would tell you the age of whatever it is you're looking at. Okay. So let's look at some examples. Let's say that we have a sample that has 30, sorry, I'm looking at my notes, 30 grams of nitrogen 14 and 2 grams of carbon 14. Okay. And we want to know how old this fossil is. All right. So the first thing you want to do is you want to add the two together, because that'll tell you where we started. Right over here, if you add 75 and 25 together, it's 100. That's where we started. If you added 50 and 50 together, 100. That's where we started. So you're going to add the two together. And we started with 32 grams. And then you want to go until you want to divide it in half. Sorry, I shouldn't just say go. You want to divide it in half until you get to the amount that is left of your parent isotope. Okay, your parent isotope is the one that you're starting with. So carbon 14 would be our parent isotope. Nitrogen 14 would be our daughter isotope. Okay, so we're going to want to go till we get to where our parent isotope is. So we'll do 32 divided in half is 16. Divided in half again is 8. Divided in half again is 4. Divided in half again is 2. And then that's where I'm going to stop, because that's what's left of my parent isotope. And then let me find another pen that hopefully works. Yep. We are going to count up the half-lives. Okay. And so that took 4 half-lives. Each half-life we set up here was 5,730 years. And so we're just going to multiply that together. My brain just froze. Actually, I got distracted by something else and then, okay. So 22,920 years is the approximate age of this fossil. Okay. All right, so let's do another one. So let's say we have another parent isotope, potassium 40, and it decays into argon 40, and it has a half-life of 1.3 billion years. Okay. So let's say that we have a fossil that has 15, sorry, grams of potassium 40 and 45 grams of argon 40. Okay. So again, the first thing we want to do is add them together because that tells us where we started. That's where I was getting the 60 from. And so we started with 60 grams. And then you divide that in half until you get to what's left of the parent isotope. And the problem will always tell you this decays into this. It may not say parent isotope, but the one that's doing the decaying, carbon 14 decays into nitrogen 14, potassium 40 decays into argon 40. The ones that are doing the decaying into carbon 14 and potassium 40 are the ones that are the parent isotope. So we divide this by 2. So that's 30, 15. I'm going to stop there because that's what my parent isotope has. And so that is 2 half-lives. And then we say 1.3 billion years times 2 is 2.6 billion years old. And that's it. There are other ways to do this. There is a formula for this, but for our purposes and what we're doing, this is all you need to know. So if you have questions, let me know.